Good evening to all. Am I audible?
Yes, sir.
Yes, very good evening to everyone. First, I want to thank AICT for approving our FDP proposal titled Innovations in Additive Manufacturing for Green and Sustainable Future. It is my immense pleasure to welcome our chairman, Dhanlakshmi Srinivasan College of Engineering and Technology, respected principal, respected Dean Academics, Dean Innovation, Dean Placement, head of the departments, faculties, professors from various institutions and industries. It is my pleasure to welcome Session 1 expert, Dr. A.K. Lakshminarayanan, sir. Welcome you, sir. I am very happy to introduce our Session 1 expert, Dr. A.K. Lakshminarayanan, sir. Dr. A.K. Lakshminarayanan, sir, received BE Mechanical, ME Manufacturing, PhD Mechanical, and full-time mode from Annamalai University. He has 15 years of teaching experience and 8 years of industry experience. His name is listed in top 2% scientist by Stanford University for the last 4 consecutive years. Also, he has published around 110 indexed articles, among that 35 Q1 journals with a citation more than 3,000. Also, he is taking editorial role in various peer-reviewed journal like Welding Technology Reviews. I welcome you, sir. Before starting the session, I request our principal, sir, to deliver a few words about the FDP. Please, sir.
Yeah, good evening, all. It's my pleasure to join with you all in this faculty development program on innovations in additive manufacturing for green and sustainable future. So on behalf of the institution, I extend a warm welcome to all the participants who have joined with us in the evening hours, where we can see the thirst among the academicians to learn and updating themselves on new technologies. So I extend a warm welcome to our speaker for the day, Dr. Lakshminarayanan, sir. Welcome you, sir. And thanks for accepting our invite and be a resource person for this session. And this FDP, yeah, thank you, sir. This FDP mainly focus on the recent trends in additive manufacturing. Hope you are all aware that additive manufacturing is playing a major role in bringing the next level. Please, can you but the additive manufacturing plays a vital role in making a revolution in the field of manufacturing. And even you can say that even in healthcare industries, even complex implants, bio-implants were designed or manufactured by using this additive manufacturing concepts. So most of the domains, they started going with this particular additive manufacturing system and the process. And the knowledge and the research towards this additive manufacturing, it's a must for the academicians as well as for the students of this generation to make it to the next level of green and sustainable. So I appreciate Dr. Rajshekharan and Dr. Radhika for choosing such a wonderful title of additive manufacturing, which is for the next generation, that is for green and sustainable future, where we focus more on eco-friendly and with the minimum waste, light materials, and all these parameters are taken into consideration. How the things can be made as eco-friendly. So today we have the session with the Lakshminarayanan sir, and we have 13 more sessions where the experts from different universities and the leaders, the top researchers who are working in different topics, subtopics among this additive manufacturing are going to join with us, and they are going to share their research experience and their findings to the academicians so that they can get enough knowledge in the domain of additive manufacturing. My humble request to the audience is take up this topic, which is a current and recently more, what you can say, more needed one for the entire globe. So please take it seriously and learn from the researchers and start working on this particular domain. And I would like to extend my heartfelt thanks to all those who joined, and I request them to take up the research on this domain and come out with new innovations which can transform the manufacturing sector itself in future. So with these few words, I extend a warm welcome to all the participants, and I wish the coordinators the best wishes for this FDP. Thank you.
Thank you, sir. Now I request Dr. A.K. Lakshminarayan sir, ESOP Chair Faculty in Welding Technologies, SSN College of Engineering, Chennai, to start session 1 under the title Basics of Metal 3D Printing.
Yeah. Am I audible?
Yes, sir.
Yes. Okay. First of all, I would like to thank the organizers and the principal DSC CET for inviting me to deliver the lecture on 3D printing, especially 2 sessions on the important topic, which we are also working in our center. So I will just share the presentation today. Just I will start. 1 second. I will just share. Is it visible to you? Or slides are visible to you?
Yes, sir.
Yeah. 1 second. One second. Is it moving? Are you able to see my slide moving or?
No, sir. It's
No,
not
one
moving.
second. One second. I'll just check.
See the slide 1.
1 second. I will just stop sharing it. Is it moving now?
Yes, sir. Yes, sir.
Yes. Thank you. Right. Though the topic is given to me is metal printing, because I am going to cover another session. Before this is the introduction session, I would like to share the overview. General overview which includes the 7 different processes of additive manufacturing. This is our campus, SSN College of Engineering. And currently, I am the chair faculty in welding technology, sponsored by ESAB India Limited. I am also heading the center, which was established recently with the fund of SSN ESAB, called Center of Excellence in Sustainable Welding and Innovative Fabrication Technology. So currently I'm heading the center. We are doing a lot of work with respect to conventional welding processes and process development and consumable development, as well as we are more focused on wire arc additive manufacturing, especially tin wire additive manufacturing, with the support of funding from ESAB India Limited, as well as through a DRDO project, which we got 2 different projects, which we got it from DRDO. Maybe in the next session, I will share that. The topic here is 3D printing from chocolate delights to concrete heights. That covers different products and different components fabricated using 3D printing. Before that, we will start with a few introduction, and then we will proceed with the actual topic. So the people who are there in the slide, they are the one now whatever we are discussing today, because of 4 of these people. So 3D printing, if you see the history, the Hideo Hudama, right? He is the one who proposed the first 3D printing concept what we call it as stereolithography. It was one of the earliest technique. Still it is being used for producing different components. But he only proposed the concept. He didn't go for uh, he didn't go for a patent. And then 1984, Chuck Hull, he patented it. He just patented it in the name of apparatus for production of three-dimensional objects by stereolithography. Uh, then the Deckard Hall in 1986, he established this process, selective laser sintering. And in 1989, Scott Crump, he's the founder of a company. He patented this technology, fusion deposition modeling, that is very widely used nowadays. It comes under one of the process defined by ASTM called material extrusion. So fusion deposition model is a patented technology. So people use, instead of this fused filament fabrication is non-commercial term people usually use. And this Scott Crump, he invented this process, and he founded a company, Stratasys Limited, and he was able to make machines. So this is a brief history of how the process was established. If you see, there are different processes which was developed over the years. These are the very commonly used process like stereolithography in 1971 itself. But that was the earlier, a very early concept and not commercialized. And then, as I mentioned, the Charles Hull patented the first commercial SLA printer. Scott Crump in 1988 first metal extrusion printer, what we call it as FDM. In a non-commercial term, we people used to call fused filament fabrication. That is very because it's patented. People use this term also. As I mentioned, Carl Deckard, he established the process laser sintering of polymer during 1986 to 1989. Then metal printers were coming up during that time, early 90s. That was developed by US GmbH Germany, and the same concept by the Carl Deckard and their team, where instead of polymers, metal powders were fused by laser. The same concept later, late 90s, the Arkham, Sweden, they used electron beam to melt the powders in vacuum. Then the process called material jetting was established during from 1990s to 2000, where photopolymers were cured by UV. That is one of the development. Then binder jetting during 1998 by MIT, some researchers from MIT, where liquid binder is being poured onto the powder bed that will act as binder. So that was the development during 1993. Later, this process is being now widely used for metal deposition or metal components metal fabrication, directed energy deposition, widely used. We are also using one of the process, WAM, what we call it as wire arc additive manufacturing, where either powder or wires are being melted, and it is used for deposition. Finally, there is one more process, what we call it as the sheet lamination. That was also proposed during 1980s to 1990, but has not come into effect until 2000. After 2000, it came for some cases. Especially even we did some work on laser lamination. We will see that when I cover something on laser lamination, friction stir additive manufacturing in the next session, probably on 28th, which is before going to discuss on the fundamental processes, why we need additive manufacturing. When we have to use additive manufacturing, that we have to make it very clear. In fact, there are three approaches through which we can fabricate any component. Here it is mentioned formative manufacturing, subtractive manufacturing, additive. Both are opposite in nature. I will just take a pointer. Wait a minute. Yeah. So formative is nothing but no metal forming operations where you have to prepare a die of the desired shape, and you just apply, you just place the billet. Initially the material what we have is billet. So take a billet of certain dimensions, just keep it over the die, just apply force from the top. So it will just go through this, and just it will come, occupy the position of the die, space between the die, and finally you will get this shape. So this is what we call it as secondary processed material. Usually any material, no, usually we use to fabricate through casting. Casting is the approach through which any primary material is being fabricated. So here the formative is nothing but metal forming operations. The secondary process mostly to have better properties, especially. So for no, if you want to change the dimensions of the product, again you need to prepare the die. That is one of the costly thing. Die is the one of the costly thing which we suffer in formative manufacturing. Even now some of the companies, even in India, I visited Super Auto Forge, where these dies are fabricated using additive manufacturing, especially laser based additive manufacturing, to reduce cost as well as life of the die. They use formative manufacturing. This is one thing. The only thing is there are two no drawbacks in this process. One is the cost of the die, and if you want to fabricate new product or with new dimensions, of course you need to prepare the die. That is the one drawback what we have in formative manufacturing. The other problem is the force requirement. The force requirement to no develop the product, that is very high. That is another problem in formative manufacturing. uh, there is another process which is also widely used, is called subtractive manufacturing, where just to take a billet, try to remove whatever excess material we have. Suppose if this is a black, this material is being removed by this is a process where we use end mill cutter and just try to remove whatever excess material we have, and finally we achieve the final shape. What are the problem in this is, few problems. One is we have to take a material, complete material. We want to remove certain material which are being considered as waste. So that is one issue. See the waste which is coming out, what we call it as scrap or chips. So that needs to be recycled. So that is one problem. Say for example, I am taking a magnesium cube and I am trying to make this component. I will end up with a lot of scrap. So keeping magnesium scrap itself, it's a tedious task. As you know, it will catch fire, especially when you keep fine particles of magnesium during, especially when you do machining. So that is one issue. There will be a lot of waste generation. So that if you want to recycle, you need to spend a lot of energy. Say for example, for doing machining itself you need to spend energy, and for if you want to, if you collect waste, then to recycle that, again you need to go for a cleaning process, separation of foreign particle, melting it through a furnace, making it into a component. Again, that uh, is a long process where you will spend a lot of energy. So that is one aspect. The other aspect is some material, what we call exotic materials, is difficult to machine. See for example, if you consider stainless steel, say for example duplex stainless steel, if you take, if you want to do machining, you will end up with certain problems. Say for example, suppose take a stainless steel of thick stainless steel, if you want to make a hole. So if you deposit, sorry, if you make a hole using a conventional tool or even with a carbide tool, your tool will undergo, because these material will undergo a property called stain hardening. Whenever you stain that material, the material hardness will go up, make it difficult to machine further. Okay, that is the problem. Say for example, if you do copper is also, when you do, it will undergo stain hardening. Okay, if you particularly machining, there will not be any problem, but when you do forming, so this material will undergo stain hardening. So these problems can be addressed when you go for additive manufacturing. So one thing is waste, other thing is if you have certain material where machining is very difficult. Say for example, duplexine is one case. No other case I can quote. If you have a intermetallics like titanium, aluminide, where we are working mostly on this. So this is a material where you can use it for high temperature, but unfortunately, the ductility of this material is very, very less. Okay, it is only 2% at room temperature. So it is not easy to deform first, then it is not easy to machine also, because the ductility is very less. For both the case, whether you want to machine, whether you want to remove certain material, or whether you want to deform the material, since the ductility is very less, uh, these two are not possible. So naturally, what we have to do look for a alternate process. So the alternate process is additive manufacturing. The other aspect, when you have a very thin section, so making from the casting further, you have to, what you have to do, cut it from the bulk casting, then you have to use secondary processes like rolling, then make it progressive rolling you have to do, then finally you will end up with a thin sheet. So these difficulties that can be overcome by using additive manufacturing. But remember, additive manufacturing is not the solution for everything. Okay, so whenever the need arises, whenever there is a problem with conventional technique, then you can use additive manufacturing. That always you have to keep in mind. Sometimes people started doing research on additive manufacturing, claims that everything can be done in additive. Everything can be done, whether then that also you have to see feasibility. So additive manufacturing is the technique. We'll see more detail. The same thing what I will do, this sample, what I will do from the top, you see, you can see a square like this at the bottom. So what I will do is I will try to do a CAD model. Maybe I will go with the slide and I'll tell you. I will have a 3D model. Then I will try to slice that into different layers. Say for example, I will have a first layer, second layer, third layer, fourth layer, fifth layer. Like that, I will just slice this. So if I slice that, I will have one plane here like this. Above that, there is another plane, another plane, another plane. So now I slice this three-dimensional into two-dimensional. Actually, this whole process as a single step I will do. For understanding, I'm telling you, slicing is nothing but make this 3D object into 2D plane. Then you just split this, make this also. Then you try to have the coordinates, all these coordinates of the particular plane. Especially I'm talking about the first layer. It look like this. When I go here, only this part, right? I will have only this part. When I go here, I will have only this, right? So I will just slice it, get the coordinates. Finally, what I have the coordinates of everything, each plane, each coordinates. Similarly, multiple layers, multiple plane. Finally, what I get is a file called G code. This code, you can run using a robot. What we have a robot in our center, or we can also have a CNC machine. We also have that. So both machines can be used for depositing material. Okay, so I'm not going to cover mostly metal today. I will cover like whatever explanation given. I will take wherever possible, I will take material into picture. Mostly I will cover what are the techniques available, when we have to use which technique. That is what the idea of this session. Maybe for the newcomer, or from any fresh, they want to start with additive, just whatever you are seeing the video is machining, right? Wait a minute, I will just So this is also excess material can be removed, right? So I don't want to play this and take too much of your time because I need to cover other topics. So first, this difference you can see just a difference in this picture, where subtractive manufacturing or machining or metal cutting starts with a block of metal, where I will remove certain material, I will create features. When I want to have a thread, I can make. When I want to make a hole here, I can make, or onto the surface, if I want to have a hole, I can make. So just remove the material, and you see there are a lot of waste material which is coming out that need to be taken care. So until the desired part coming, so you will end up with final product is this. Whereas additive manufacturing starting, no, it starts with nothing. You have only a substrate plate, no, or even polymers where you don't want anything. You just have a build platform that is not a consumable there. You just take that platform and start building layer by layer. So gradually add layer by layer. I have a few more slides which we make it very clear. So gradually add layer by layer until you have the desired product. Okay. So if you see this, uh, this is subtractive. When you say additive manufacturing we use, the energy is reduced by 50%, and please remember the cost of the material is reduces up to 96% when you compare to the traditional additive manufacturing techniques. Especially since the scrap is not there, whatever dimensions I want, that I will get. In fact, in many cases, the property is also better, almost matching with the conventional secondary processed material. So it has open up now wide opportunity for whoever start research in additive manufacturing. So most of the in the wherever possible, I will give some idea to extend your research also, probably in the next session. So before going to that, no, we just take two different terms which is interchangeably being used by many of us. One is additive manufacturing, other one is 3D printing. So this topic, whatever I am presenting with the topic 3D printing, in some places I use additive manufacturing, but 3D printing is very colloquial language people use. But technically, industry point of view or manufacturing process point of view, additive manufacturing is the proper term which we have to use, because it compares with the conventional processes like subtractive manufacturing or formative manufacturing. Basically, this is the definition given by this committee, ASTM for F4291 committee during the year 2009, and they have given this definition. So additive manufacturing, you just is a process of joining materials to make the component from 3D model data, usually layer by layer. This is holds good for 3D printing also, but 3D printing is a very general term which covers many of the process. Say for example, fabrication of object through deposition of material, uh, using a print head, nozzle, or any other printer technology. So this is a very general term, but this is more technical term, additive manufacturing, which we may use. So, as I mentioned already, it takes digital input in the form of CAD model, and just to create three-dimensional part by layer. We will see from where we have to get. Once you have 3D model, once you have G code, so the process is like this. So deposit layer by layer. This is the in between steps you have. Finally, what will have this for having the data, the G code. You can also visualize the features FDM. Maybe I will cover that. I have few more video for you just to understand the capability of 3D printing. So initially we need to have a 3D model. Then you just do slicing. Maybe there is a spelling mistake. You will end up with the G code format, and you will be doing 3D printing. Once G code is ready, just transfer the G code to the machine through either Wi-Fi or through a memory card, just transfer the file, and just you have to do certain settings for whether you want to have support, or what is the shape of filling, whether you want to 100% fill, 50% fill, like that we have something. Then you just do the setting and try to do 3D printer. Okay, so finally you will get a project. Those who are at the initial stage, I recommend to go buy a 3D printer. So it costs only FDM for polymers. It will cost around only 20,000 rupees. We are spending a lot of money for, even for phones. So it will cost only 20,000 rupees. So you can buy and learn plenty of models which I'm going to show now. Okay. so so what we have initially, you need 3D model. So how you can get 3D model? So for if you start with a hobby, then you can explore this website Thingiverse, where you can get the models, like whatever model you just type there, you will have very beautiful models which is already people have done. And because of these websites, we don't want to spend too much of time for understanding 3D printing, especially if you want to learn as a beginner. So directly you can just try to get a model from this is one way. And this is a solid model. No, you can just print 100% fill also, or if you don't want 100%, you can start even 20%. If you are, there is no load bearing member, only these are for aesthetic, or just for presentation, you can just make whatever. This is a solid model. uh, uh, this is called, you can search even in Thingiverse. You can just try to search this term Varnai, where this is a hollow, the surface also you will see hollow. This is a very different parts you can make using this. You can search this and just get lot of models available in the Thingiverse. There are plenty of websites. Directly you can just get it, but you have to do your printer setting, and then you have to print. This is one more model which is very popular. What we call it as, you just search articulated. What you can just articulated models. Just type articulated. Then sorry, some problem in my pen tab. Okay, so directly you just no, you can see link. Suppose remember, I want to make a element chain, like a chain, right? What I have to do conventionally, if I want to do manufacturing, even as a metal or plastic, take a metal. If I want to make a chain of stainless steel, what I have to do, I have to take a bulk material, extrude it, make it to very thin section no, of wire. Then then from wire I have to do some metal forming to bend it. uh, then I have to do some welding here. That is how usually, if you want to fabricate a chain, you can do that. But 3D printing, if you use this feature, this consists of lot of links. That link can be directly printed without anything, any problem. All these I have done a lot of work. Even in front of me I have two 3D printers in my home. For hobby I bought it. So this kind of link, if you want to generate, what we call it as print in place. Okay, print in place. I will show you some videos for that. Print in place. Okay, so directly you can print if you have this. Before that, no, this no clip, whatever you are seeing here, two things you have to notice. On the right side, I'll just take a laser pointer so that I can, yeah. So this clip which shows a thread cutting using conventional machining process, turning. Here, the same thread you can make using 3D printing. The approach is here, these two. One is bottom down approach, where your material is being removed. In this case, just you understand, just to take a plain rod, try to remove material from top to bottom. This is a top to bottom approach, whereas here, it's continuously deposited. The very important thing what you have to notice is, here you can see the chip which is coming out is a waste, you need to recycle. Whereas here it's whatever material is 100% is being utilized. Maybe some material is being lost, especially when you have support element or something when you need. That is a difference, basic difference between additive and subtractive. So now additive manufacturing or 3D printing, you can use it for different materials, starting from metals, sand, concrete, even with human tissues. Probably I will cover plenty of application instead of theory. I will show a lot of application, and before that I will try to explain these 7 processes. These are very important processes we have to understand. This committee, ASTM 4291 committee, in order to have globalize and we have to follow certain standards across the globe, they classified additive into 7 categories. Number 1 is VAT polymerization, is a resin based printer. Material extrusion, that is basically you can use wires or pellets, even paste that can be extruded through a nozzle. So then powder fusion bed is very popular, which uses powder and try to melt with your laser source or electron beam source. That is one process. You can use this for metal, this for metal. Material jetting is also one of the process where material in the form of droplets, which will be from the nozzle, which will come out. That is one process. Binder jetting, where you use binder particle. Just you have a lot of powders where the powder binder will be sprayed in between to create bonding. Sheet lamination is nothing but take different sheets, instead of powder or wire, take different sheets and try to bond it, instead of because when you take powder or wire, it will take a lot of time to deposit. Okay, directed energy deposition, maybe I will go in deeper when I show some video for your understanding. um, um, Directed energy deposition is nothing but I will be using a laser source, or this may be laser source or electron beam, EB, or any arc. Maybe I will cover that arc processes in the next session. What I will do is in directed energy deposition, I will just place the wire in the arc column or laser beam or electron beam and try to melt, and I will just deposit onto the substrate. It may be wire, or coaxially I can just feed the powder to deposit. This is called directed energy deposition. Why it is called directed energy? Because other particle like powder fusion bed, you will keep the powders at the bottom in the just to build a flat form, just to try to use laser and melt. Whereas in directed energy deposition, you are directly feeding the raw material into the source, arc source, heat source. Okay, that is why it is named. So if you see 7 categories, still there are a lot of subclasses. Say for example, in VAT polymerization, you have SLA, selective laser stereolithography, where you will use laser. Sorry, wait a minute. I'll just some problem with. I'll just clear it. One second. Sorry for the interruption. So here the laser, point by point, you will screen and try to cure the polymer. Whereas in DLP we will be using a projector, like what we use, projector for screening for presentation. So it uses projector that will scan a whole layer. This is a point by point scanning stereolithography, whereas DLP is a layer. Each layer is completely cured, at a time. So LCD, also it is other technique that is widely used, in the printers, available in the market. If you see, LCD models, you can buy it for even 15,000 rupees. that you can practice. Okay, that is you can just search. There is a model called Halat, used by manufactured by Creality. It's very cheaper. You can buy one 20,000 rupees FDM or FDM machine and one LCD type machine to practice initially and to learn many things about 3D printing. There is one more process, what we call it as continuous liquid interface processing, where there is a layer. Only all are now using same principle, but only thing is, some improvements have been done. When you compare LCD with the DLP, the speed is much faster. They will use a LCD and a LED array, so that wherever it is not required curing, that will be masked just as a switch on and switch off the LED array. By that, it is much faster than this. When you see clip, sometimes when you pass light through this lens, there is a fluid here. There is a chance of sticking with the lens. So to avoid that, there will be oxygen layer introduced in between, so that it will not cure at the near the lens. So that is why this is novel as you compare to the other. There is a slight modification. The concept is very simple. You will be using a photo polymer and just try to pass light and just cure it. Okay, that is the idea. Whereas when you consider the next process, again you have a lot of other process based on this. FDM and FFF already I shared. You can even use, instead of wire, you can just use pellet. Pellets you can use, just heat it, just extrude through nozzle. You can also have direct ink writing, that is also very popular. Both can be used for bioprinting, and concrete printing is one of the areas where even in India, Dubai, they build houses. Even IIT, some IIT, they build a model house for that to demonstrate concrete printing. I have one video which I will try to show. Material jetting, again, the material is in the form of jet. They will they will droplet of material they will create and they will deposit. You have two different models, polyjet and multijet, where polyjet, multiple heads instead of single head, you will have multiple heads, where no, you can go for multiple colors. That is also possible. Binder jetting, as I mentioned, you have again stand binder, metal binder. Based on the application, you can just use both. Whereas powder fusion bed, you have selective laser sintering. Maybe I have one more slide where I will just clarify that. Selective laser melting are 4 different categories. Uh, Direct energy deposition, you have laser metal deposition, electron beam. There is one process called lens, uh, that also very popular. No, near net manufactured, no, laser engineered near net manufacturing. What is mean by lens? That is also very popular. Laminated sheet object manufacturing is just use some adhesives, stack layers by layer to achieve the component. That is LOM. Ultrasonic is used for very thin sections. You can same concept, take sheets, use ultrasonic transducers to create ultrasonic vibration, so that friction will be generated and that will be used for bonding. One is missed here is called friction stir additive manufacturing, which we did some work in our center. We are working on creep studies. So this is first material extrusion. Each category we have certain thing, what we call it as resolution. Resolution is nothing but after deposition, if you see the surface, if you think it should be like this, it is not like that. You will have always this. So this resolution is very important. In case of material extrusion, you will achieve 100 to 600 or 800 microns based on the nozzle diameter. So this is of low cost. Maybe I will just play this video. So it's like a hot glue gun. No, we'll just deposit. So basically, it is low cost. It works well with thermoplastic, composites, concrete, biomaterial. Lot of open source system is available. You can develop your own system your own development, because basically all these 3D printer used for plastics, they use either Merlin software or Clipper. There is a software Clipper. They are all the Merlin is open access. You can just download, and just you can create your own systems. That is one second, I'll just stop this. So if you see variants which I already shared with you, application prototyping, if you want to do some projects, you want to develop prototypes, that you can do it using this process. All biomedical applications, you have a lot of applications, even tissue manufacturing people are trying, though it is not commercially available. People at research level, they have gone to a certain extent. Only thing is the material, whatever you deposit, the anisotropy with respect to the build direction, the property may be different. The surface finish, the nozzle diameter in conventionally used polymer printers, most of the time we use 0.4 mm. So that causes you need surface finish is not so good when you compare to SLA process. So larger speed for larger parts, it is difficult. Nowadays we have a lot of since Clipper software and some modified softwares are there, so they are going for higher speeds. Printers are available. So this is the one of the method, fused deposition modeling. You can have single head or multi head. You can just pass the wire and deposit, just based on the technique whatever I told. Just try to deposit. So basically you will start with the single layer. Two things you can hear the movement. The movement, most of the time z axis is controlled in the nozzle. So here if you see the nozzle, it will move only in this direction or this direction, uh, whereas bed can be moved both the direction. Okay, but conventional printer, no, the nozzle will go whatever we have, the plastic printers, polymer printers, no, it will go up and down. This movement is also there with the head. Only this y-axis is this is usually the y-axis. Okay, so the y-axis is you can move the bed. The nozzle X and Z can be controlled. No, this way, right? So basically no, according to your if your first layer consists of this rectangle, so it will deposit like this. You can see some gap is there, that will affect the structure. So you just see how, what are the possible way, possible models you can just print. This is a octopus where if you're if you have some links, then it is easy to print. So they are print in place. Sometimes you can just print and assemble also, like what he is doing. Depending upon the size, the time will be different. You just imagine what are the ways by which you can just print it. This is separately the body and the limbs, they are separately printing it, then they will assemble. That is also possible. Accordingly, you have to design. Even these models are available in open source. You can just download it. According to your printer setting, you have to modify the setting and just print it. So multiple heads, if you have multiple heads, still it is possible. You can just print multiple heads. See how nicely horizontal hole with even threads. Nowadays, no modeling threads and all easy. So you can just this way you can multiple colors if you want. No, you don't want to. You need not have no multiple headers. Instead, print with different dimensions. no wires you change and then assemble it. So all are this link based. Okay, you can do a lot of butterfly or whatever. Even for our prototyping, you can just do that. So these are some of the models just for the capability, right? I just want to show the capability. Sometimes you need to do post processing, like polishing it. You can give different colors also through painting. Right. So that is regarding FDM. No, I witnessed. I hope different components can be done by using a wire. Then this process is a resin-based process where you will just cure the resin. Just you have a building plate, so you have the resins filled in. So from the bottom, no, either it is a LCD screen or DLP printer or clip, all uses the same concept. Yeah, only thing is there is certain difference between them, among them. So you have a build plate where at the bottom you have a resin. Through the lens, I will just send the UV light, so that the first layer, no, there will be, I will just maintain a gap between this initial gap, what we call it as layer thickness. So layer thickness. uh, so once I keep this plate at the bottom, so initially here I will keep certain layer thickness, then I will just cure this. One layer is over, next layer just move the platform up. Then next layer you can see second layer cured. Like that it will go. This is one of the system where simple system you have a ball screw arrangement with a linear rail. Just this will move your building plate upward. Uh, it is not the only way by which you can deposit. So if you see this model, so initial layer will be here. So because the initially your building plate was at the bottom, so they will just keep on moving upward. Not necessarily only upward, you have other systems available. This is very common. No, this is only, if you search in the net, you can just buy it for around 15 to 16,000 rupees, and you can try and learn 3D printing, especially resin type of printing. Okay. So the polymerization, I don't want to deep into the theory. Maybe I will show a video so that your understanding will be better. But few points, only very fine microns. As I mentioned, there we starts from FDM 100 to maybe 600 microns, whereas here it is resolution is better because it is based on resin. Your that means resolution is fine, means you will have very small features in your product. That is the advantage of this process. You can see it is the best surface finish. It will provide the best surface among all AM processes. You can have very intricate details transparent parts you can make, and very very fast, especially the last one clip, because there is a special technique. You have a lot of application maybe which I will cover very soon. So these are the trade names for that, which already we discussed. Basically these three are very common: SLA, DLP. Recently clip is also one of the process. Only the source is different. If you see the first one, here we use laser, the selectively cures the resin. It will take a lot of time. That is why this comes into picture, where this entire layer is being cured all at once. Laser LCD helps us to control the system better, and hence you will make it slightly faster than DLP. So these are the system available in the market. Uh, Basically, different manufacturers are there. Anycubic or Eligo or Prusa. Creality is also very popular. The cost earlier they had a version LH or LD002. Now there is a system called Halat. You can buy it 16,000 rupees or 17,000 rupees. It will come. So basically the concept is very simple. You have to prepare the resin. You have to just pour it in the container, what we call it as vat. That is why vat polymerization, the process itself, name is vat in general. This container vat, you have to pour it, then bring it to the first layer, cure it from the bottom. The source may be different. Maybe you have laser source or LCD or whatever source you use. The same concept is there. Maybe I will go, before going to the video, just I will share two things. One, there are two ways you can just deposit material, or you can build your component. Two systems. Whatever I showed up to now is this system, where your blood fabrication platform or build platform initially at the top. So bring it to the bottom, just near to the lens. You need to keep the thickness of the first layer. From the bottom you will cure. Once the first layer is cured, then slightly you move up. That means you have to keep the layer thickness, second layer. Then you have to start, because already one layer is cured and it is attached to the build platform. So next layer will be cured, and again it will be adhered to the first layer. Likewise, no, you have to go up. So this is the one which is very common. There are other system which is also there. The build platform, no, it is at the top. You have to pour the resin, so that the space from the top and the build platform is the thickness layer. So initially from the top you have to start curing. So first layer will be cured, then it will go inside. After that, one layer is over, it will it will go down with respect to the thickness layer. So next layer, next it will go, third layer will come, fourth layer. So it will immerse continuously, it will be immersed in the resolution, resin. Finally it will take out. Okay, this is one method. So either you can go bottom up or top down. But basically, most of the machines or commercially available machine uses this. Both systems are there. So maybe I will just play this. They are filling the resin now. Just they will fill the container with the resin. Now 3D printed. From the bottom you can just the build platform is there. Initial layer is being builded up, so it is going up now slowly. But it's made faster, but it's not going like that. You can see very fine feature and surface finish of the component. That is much better when you compare with the FDM. So maybe I will this also. This is from the top. That's it. So this is as I mentioned, each layer. Oh, sorry. Each layer here, if you can see, some void is there. I'll take pointer. Sorry, this void is there. There will be no interfiber bonding region where here or here. This is how the internal structure will look like fusion to deposition modeling. Whereas here, usually you have reacted regions between each layer. So that is how the bonding is there. The next process, what we will see is selective laser sintering, usually which uses CO2 laser to fuse a small particle, like it may be plastic or metal, ceramic, glass powder, whatever it may be. So you have to spread the powder, try to melt the powder with respect to the your model and according to the coordinates. Then your first layer, then your fabrication piston will go down. Maybe I will have very better. I'll have a better picture to show you very soon. This is how it works. So powder leveling will be done first. Then laser melting, your platform will go down. Maybe I will show one more slide which you will have very good picturization. So usually laser or e-beam means electron beam, layer by layer. The resolution here is 20 to 100 microns. This is another advantage. The very biggest advantage is you can have fully dense component and very good very strong component. That is also one of the advantage of this laser sintering. Metal, polymer, ceramic, all are you can do variants. You have SLS, uh, SLM, DMLS. Yeah, all concepts are same, but we have to understand. uh, I, I don't know why they call it as sintering, and most of them there is no real explanation for that. All these processes, whether it is a plastic or metal, there involves melting. So always there is a melting and solidification that is there. Though it call it, whether you call it as directed metal laser sintering, where metal is being melted, I mentioned it here. It's full melting. Uh, electron beam melting is very popular, especially for reactive materials. Maybe I will cover that in the next lecture. Just try to understand, this is how the actual component. I will show one video. There are 3 chambers, where one chamber where we will fill the powder first. The next chamber is a working chamber. The other chamber, whatever you see here, I can just mark 1, this is 2, and this is 3. Initially powder leveling is the first step, where whatever powder, this platform slowly it will go. Initially it will at the it will be in the bottom, so it will be completely filled. So it will, when it comes up, there will be excess powder above this level, where this roller will come and it will fill here. This initially it will be at the top. Maybe we will give one layer thickness space, so powder will be deposited or spread by this roller. It will just whatever excess powder available here, because it is going up, so that will be spread over here. And for one layer thickness, then you will be doing laser melting on of that particular layer. And whatever the excess powder, once it is melting is over, whatever excess material, it will be moved here. This when because it is getting filled with the excess material, so this will go up, this will go down, this will also go down. It will collect the powder, excess powder, where this is a working chamber. As it goes down, what is the thickness it will go down? It will go down with respect to the layer thickness. Okay, this is how again powder laying, this process. So powder laying, laser melting, powder laying, again laser, it will work like this until you will end up with the final product. Maybe I will show one or two videos, so that you will understand it better. You have to do global spherical powders, usually 10 to 50 microns powders. Just pre-place it. This is the difference actually. Pre-placed powder is here. In case of directed energy deposition, we are feeding the powder through the source. That means heating source. That is the difference basically. Whatever unmelted powder or unsintered material of previous layer that will be collected in the collection chamber, then it can be reused. I'll just play this video so that you can have some idea how it works. This is powder layering, then laser is being done, it is going down again, the platform will come up, spread the powder, laser melting is there. This process will continue. Finally, you will end up with this particle, this component. Okay. So maybe I will just do one more video. That is the schematic, animation. This is a real one where how this is also another advantage. In a single same platform, you can go for multiple products of multiple dimensions. Maybe I will play it again. So that is also another advantage. It's not like other process where different geometries, if you want to construct slightly, it is difficult. SLA you can do that. FDM it is difficult. Here it is not only in single layer, you can stack, in between you can have space. The powder itself will give a support, and multiple layers also components you can make. For example, first 100 mm I can make a component, then I can have a gap of 50 mm, then another 100 mm I can make a component. Like that I can do that, right? So this is SLA. One video is there. I will just before maybe I have another video I will show there. This is material jetting. That is the next process. You have like material jetting is not very much similar to what we have in printers, right? Inkjet printers. Similar to that, you will have a head where jet of particles, photopolymers. So that will be forced to come out, and that will be deposited onto the build platform. The interesting thing here is the resolution is 16 to 30 microns. You will have very good surface finish, and multicolor, multi-material, even transparent. These are the advantage of the system. Dimensional accuracy is excellent. But material, whatever you produce, that is not so strong. That is one of the limitation. It is being used for preparing models for demonstration and prototypes, for realistic look and feel. For those applications, usually they do that. This is also, I hope this is a video, it will play. It's like an inkjet printer. You can see how it works. The process works there with a small animation. Just a droplet is once the droplet is coming out, it is cued by a UV light. So this is binder jetting. Again, the resolution is given 50 to 30 by 300 microns. Large build volume is possible. That is one thing. Only thing is, it's like a powder metallurgy route where you can just prepare a green compact. That is not so strong. You need additional sintering. Whenever you do green compact in powder metallurgy, usually you need to go for sintering. So just this will help us to understand the process. But only thing is you need a secondary process. Again, you need to do sintering. This is only like a green compact. Yeah. So this is directed energy deposition. Slightly you can see, so far we talked about microns. You see here the resolution is in the range of of 0.5 to 2 and 2 mm. That means 500 to 2000 microns. That is one of the drawback of directed energy deposition. But unfortunately, this is very useful for metal 3D printing. You can go for repair work also. If you have some parts where you have cracks, you need not throw them out. Instead, you can just deposit certain, you just remove certain material from the crack where it is there, just deposit certain material, so that excessive, expensive parts can be still used in the applications. So that is one thing. The other thing is advantage over other processes. Large volume deposition is possible using directed energy deposition. Also, multi-material, compositionally graded parts, where we are more concentrating on that in our center. Maybe I will cover that when I cover those processes with the videos what we have taken in our lab in the next session. So the trade name for powder fusion bed, uh, as I mentioned earlier, whether it is a polymer or metal, all these cases, this is the scenario: melting and solidification, not the sintering. Okay, people have used that term maybe to have different trade names, but the actual scientific thing, what you have to understand is it is melting and solidification, not the sintering. Same thing. One video. The same thing which already we discussed. Just to refresh. Yeah, this is powder. So to summarize, we have 7 processes already discussed. Wet polymerization uses liquid photopolymer that will be cured by UV. You have different variants of that: SLA, DLP, direct light uh, projector, or LCD, clip, continuous laser, no liquid interface processing. Application, if you see, dental, jewelry, prototypes, all are there. You just maybe this is available in the net, you can just go through that. Material extrusion, again, you have all these already be discussed. You can just check the application prototyping. Material jetting is for multicolor model. Dental molds. Binder jetting is for metal parts. You can go for post sintering, as I mentioned. Large prototypes also is possible. uh, this is very commonly used for uh, 1, 2, 3, and 4 is very commonly used for metals. I'll maybe in the next lecture I will cover some of them. Just to have some comparison, wet polymerization is best accuracy and surface finish. Material extrusion is most common and cost is less. Material jetting you can have for different colors, multicolor printing, like our color printers. Binder jetting, low cost powders and for large scale. Powder fusion bed, strong, functionally graded materials and polymer parts. DED, direct and large volume deposition, and if you want to go for a repair work, you can still use that. That is one of the advantage of that process. Sheet lamination is fast and low cost prototyping, especially suppose I want to have some model of large dimensions. Okay, no, if it is a regular shape, it is no waste of time to use regular shape to deposit using powder or wires. Instead, directly take that block and try to bond it with some hybrid process, like a hybrid additive and separative process, which will also which I will cover in my lecture at the later next session. So with that, we covered 6 processes. Quickly, we will have other applications and no nothing. This one is chocolate. So we also in our lab we are fabricating one chocolate. Maybe within this month we'll complete that. So you can print your if you want to have to celebrate your birthday or your friends, you just model it whatever dimensions. Even you can print your face with the chocolate. Lot of videos are there, you can just search and learn. now that is why my topic started with chocolate delights. Now even food for elderly people, I will show one slide where food, easy chewing, foods can be printed using 3D printed, but whatever material you use for extrusion and all, that should meet the food regulation standards. This is one interesting thing which we can understand. Now you can print your home very quickly, not like in usually take years to build your home, but with the advent of 3D printing, they are able to build much faster than what usually they do for building in the house. So this also comes under material extrusion. Uh, the quality and strength, which is also very very good as you compare to the conventional processes used for constructing your building. Whatever shape, no shape and everything, curvature, if you want to create, it's not so difficult to build your building. So this is that's why these two topic which I have taken it in the slide title itself. So if you want to build from chocolate to concrete heights, you can do that. Nowadays, a lot of dental application where all of us have they have our own sizes and geometry that can be easily 3D printed nowadays. No, you cannot wait for several days to just modify your or if you want to fit new things, you can easily 3D print and just deposit. Ongoing research is there, bioprinting of teeth and gums, all these dental aligners, Invisalign, that is all that can be easily printed with respect to the shape and geometry of each and every person. That is a very very useful tool nowadays for dental applications. So you can also use implants, now even titanium implants or the dental orthodontic wires, those surgical gates, all can be printed nowadays. Either it's a metal or polymer or even alloy that can be done. Titanium, because the geometry, if you want to prepare titanium, also the ductility is very less because it is a HCP structure, hexagonally closed pack structure. Mostly whenever you see material with hexagonally closed pack structure, always the ductility is low. It is very difficult to make those components by metal forming. That is why if you take titanium screws and stainless steel screws, the titanium screws are much much costlier than if I want to insert my teeth, uh, any tooth, then the cost maybe for titanium it is around 15,000 to 20,000, whereas stainless steel is much 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 lower. So this is one application. Orthodontics is one application is coming up. A lot of work has been done already. I'm just sharing some points. Uh, if you see SLA, selective stereolithography with the SLS, the surface finish you can see much much better in SLA and SLS. Basically, as I mentioned, since you use wire and nozzle of 0.4 mm, usually 250 to 800 microns nozzles if you use, your surface finish will not be like this, whatever you see here in SLA process or industrial SLS process. So it will look like this. Still, you can control this. You can do post processing also, but directly, near net manufactured components are better, which avoids post build operations. So right now it is used for cardiac surgery, patient specific heart models. That is one area. Neurosurgery rehearsals are being carried out now. Even the facial bone reconstruction for patient specific, because these jaws are shapes and jaws are everything is different for different people. So they will try to model it, use 3D scan and try to do that. So while I told you about the models, One way you can take it from internet. The second way, you can model it on your own. The third thing is, just if you have any three-dimensional object already, try to do laser scanning, just get the model, then do the reverse thing. Again, you have to slice it, get the coordinates. These three ways you can just try to get 3D model. No, that can be used for these applications. So some material, no, sometimes no, your skull injury, if your skull is got damaged, and that it is being replaced by no, that is some proposals are there. 3D printed components. What no, they use usually bio compatible materials like titanium or ceramics, hydro acceptite or zirconia. They are no, which will mimic natural tissue. Um, Even people know looking for magnesium based alloys also, because magnesium is biodegradable and no bio compatible material, where our body can dissolve no magnesium, but the only thing is you need to extend the life until the patient is getting cured. Before that, if it get dissolved, that is not good, it's not desirable. That is why people trying to develop magnesium based components. Okay, so this is one application where patients, because especially diabetic patients, the shoes and insoles, they are being tailored based on the foot autonomy of the patients, so that wherever you want, wherever which area of the foot are being affected, please, whoever is attending, please unmute yourself. If you have questions, then we will discuss at that stage. Please mute your audio, please. So, otherwise, organizer try to mute them. Okay. So, each patient will be, they will have getting affected in particular region of their foot. So, accordingly, you can design. And
இது பே பண்ணுமா பே பண்ணிட்டீங்களா
is there anybody who is talking? Okay, wait. Maybe yeah, right. So prosthetics, as I mentioned, that is one application. All 3D printed jaw, our bionic ear, uh, those being printed. This is one application which I have taken it from the net. 16-year-old boy who got prosthetic arm less than $100. That is also one of the application. These are now some interesting sculptures. If you want, you can build. I built my own, this statue of particular size in my printer. And only thing is, you need to learn something from how to modify, your shape slightly to get the real picture using Blender. So maybe it will take some time to learn Blender software. Uh, that is only one software which I know I am telling you. Just use Blender and try to learn that. There are a lot of tutorials available. Then another skill you need to learn is painting. So for these creatures, if you create, you need to go for micro level painting. There are kits available, but they are costly. That is why still white color I have my own thing. I need to paint it. These are some of the interesting thing. If you are a hobbyist, you can try that. So the gold and the jewelry manufacturing, it is conventionally it is restricted to the ideas of the person who is doing that. Very complex shapes cannot be done. You conventionally, it is very difficult. Traditional methods, it's very difficult. Complex geometry can be done by using 3D printing, especially small batches. So some people know customized product if you want to make for seasonal sales. For that, you can manufacture jewelry products using 3D printing. No, high details. No, you can have very small features you can create. Even you can create your face in the jewelry. That is also possible nowadays. Soft air molds, this is one problem. No, all of us, even if you see any student or even our we used to put always headset, air pads. So it will always apply pressure on your, the air, so that anatomy, it will differ, each individual it will be different. So just measure it accordingly, you can create the, mold, and each one can use these hearing aid shells, that will help us to, protect our ear, since we are continuously using this. So you can create your own drones. If you want to develop drones, some product is getting damaged, then you can directly print it, and just, even these propellers blades. So most of the time, when the drone gets, just when it fall down, it will break. So my students usually print it, and just they will go for, just assembly, then they will reuse it. So this hybrid part by the Urubi, right? This is the company, though they used 50 parts, 3D printed parts from plastic, make it lighter. This person is sitting, the whatever you see, this, even the white color is also, 3D printed. It is more cheaper and environment friendly. Recent days, bioprinting with the living cells, uh, bioprinters, human organs, they are doing a lot of research, especially to print, the stents, for, once you do, there is a hard problem. These capillary and blood vessels, as well as some are working on, even modifying the part of human liver, just by bioprinting. Cell level printing, now it is coming up, not at a very big commercial level. Even now, we can create a makeup kit. This Mink is designed a printing makeup kit. You can choose your own color or whatever you just play with that. You can do it on your own. This is one of the for boots. The Nike, they developed a prototype with a shorter period time. Whatever design, changes, you can do that. It can be done within hours instead of, multiple days. You can just print in hours. That is the advantage of 3D printing. As I mentioned earlier, people who are not able to chew it, so chewing problem is there. There is a company, Smooth Food, uses 3D printing technology to just turn the fresh ingredients into chewable meals. So this is just imagine, wherever, no, whatever application we see, we can see 3D printing. This is very interesting. Construct, they used, dresses, they, fabrics of different styles, they printed it, textile printed, you can use 3D printing. If you see this flight by British Royal Air Force, uh, they use a lot of products, 3D products, 3D printed products. Maybe they will implement that for almost next year. They will earn this much, whatever mentioned amount there, it is there. Basically, I will just end up with what you need to have is, you need to have a model in STL format, uh, standard triangular, format. Basically, it divides the coordinates with a triangle kind of features. Uh, then you will be this model will be fed into a slicer. Common sizer is Cura, you can use it, but wait a minute, some problem. So okay, Cura, but each and every printer comes with its own slicer. Creality, what I use, it has its own slicing software, better suits for their machine. they worked for that. Then just feed that file G code. After that slicer, this is a 3D model. Then after slicer, you will end up with 3D G code. Okay, so that will be fed into the system, and it looks like this one. Maybe all other factors. Just quickly, I will go through that. Another 5 minutes. I will take 10 minutes. We'll have discussion, or whatever time we'll extend it. So resolution, you can play with that. Thickness layer you can control. If you have very good resolution, if you want to have, then relatively the printing time will increase. That is known fact, right? Suppose if I want to build 10 mm, if I use 0.1 mm, I need to go 10 layers. Suppose same 10 mm 0.2, then I can go up to 5 layers. Like that, as the number of layers, your printer head should move different number of planes. So naturally, your layer height decides the print. And this is also important. Outer initially, whether you need to have outer shell, what is the thickness you want. All these, you can all. What is the fill pattern? That is also plays a vital role. Fill density is one of the very important factor which decides the strength, that we can play. Even 100% film, 100% also you can fill it. Again, slightly the time will be higher. And how no these are some of the different filling geometry, where mostly this is being used. Grid structure is being used. Other thing we can use it, but accordingly the time will be different. Okay, so this is very common. Grid method is very very common, which we use. Sometimes if you want to build a structure with overhanging, you can see just this is attached to the bed. But after once this layer is, maybe I will check different color. One second, I wait a minute, wait a second. Yeah. So once this layer over, this layer is deposited, next layer when it deposit up, there is no problem with this layer up to this. When your printer head moves here, this area, you don't have anything to do, support the your liquid metal which is coming out. So or the wire, whatever the semi-solid state wire it is coming out, it will directly just fall down. So instead you will just create a support. This is of very loosely packed. This is not of the same density of this. This is of different density. Still you can play with the different formats or different geometry of your supporting member. Once it is deposited, once your component is finally finished up to the top layer, then you can easily remove this. These supporting members are that is why it is not near net manufacturing or 100% when you have support. It depends on again on the model. No, same product, just imagine same product, can I print without support? Yes, you just flip the no model and do the slicing. So naturally any overhang, please remember. So since keeping this here, since you are keeping this no overhanging, you need to have support. By arranging, by having proper arrangement, still you can avoid support. The same product, you can just flip that just and keep this up, this this place, you keep at the bottom, so that this support member is not. So when you start, whether you want to start directly the product or you want to support, give some support, because you Pune State Park. So printer even that one that one drop inner like part of this application is being different. Okay.
It may be some signal delay. Participants are requested to wait for 2 minutes. Can you hear my voice properly? Yes.
So whether you have seen my last slide. Sorry, I got disconnected due to my one phone call.
No, sir.
Last slide you didn't see?
No, sir. No.
Wait a minute. I'll just go to that. Which slide we left actually without hearing? One second, I will just share. Whether you seen that Creality printer? Okay, maybe next session I will take. This is our center. Maybe I will show. Is it the slides are visible to you?
Yeah, sir. Yeah.
Yeah. So this is our center where this is a robot, and we have several welding machines from ESAB. We have machines from Miller Dynasty 350, and we have machines from Lincoln. All this is being used for additive manufacturing. We are doing a lot of work, industry-related works for welding-based, welding development, process development, and consumer development. So I will cover those metal additive manufacturing process in general. Also, whatever we are doing, that I will cover with you in the next session. So right now, I will just hand over to the organizers to have a discussion on if you have any doubts or clarification.
Hello, sir.
My sincere thanks to Dr. A.K. Lakshminarayan sir for the detailed technological overview of 3D printing and additive manufacturing. Now the session is open to participants to clarify your doubts. Please.
Hello, sir.
Yeah, please.
Good evening, sir. Session was very
Good.
nice, sir. I just want to know about the how to improve the surface finish while using FDM by using PLA or ABS.
See, surface finishing. See, one thing first is you have to calibrate your axis. Okay, there are several steps to improve. One, I will tell you one by one. So first step is you have to check your axis whether they are parallel. First, sometimes continuous usage, they are made up of screws, ball screws or whatever lead screw. So you have to first calibrate your axis, x-axis, y and z. First thing, and you have to tighten your belts. That is, sometimes if it is run by belt, or sometimes it is run by screw rod. So both you have to check. That is first step. Next step is you have to check the how much wire is coming out. Say for example, you have to allow 100 mm wire to come out, and you have to measure whether actually 100 mm is coming out. So that is very important. Sometimes you set 100 mm, you may end up with only 95 mm which is coming out of the extruder. Okay, so that you have to calibrate. This is these are two very important steps before your model is going. You have to print it. Okay, that is two things. The other thing is also sometimes your bed is not so sticky. Okay, axis calibration is very important step. Next step is extruder calibration. Okay, these two steps if you follow, that is one thing. Sometimes if you buy a filament PLA, if you keep that for 3 months, sometimes it will deteriorate with respect to time. Okay, to avoid that, what you can do is initially if you print it for print with a temperature of 200 degrees centigrade, what you have to do is slightly increase the temperature. You can control bed temperature. Initially you might have used 60. Now you can slightly increase. If it is not sticking to the bed, you can slightly increase to 65. Or say up to say 100 you can go, but 65 is sufficient bed temperature. Then you can slightly increase the heater, the extruder temperature. Say for example, initially if you use 200, Now you slightly increase to 210, 215, because as the filament is getting older, sometimes this problem I faced. So I used these techniques to make it proper, so that your flow is coming out, whether your the set values are working as per the set value, that you have to check. Okay, one is control bed temperature, control extruder temperature, calibrate axis, calibrate extruder. These things if you do, then you'll get a very good surface finish. Okay, I maybe I don't have right now. I have a lot of components with excellent surface finish in FDM. Okay, only thing is, and it depends on the filament also. Sometimes which filament you are going to buy. No, somebody will sell for 500 rupees, 600 rupees. You buy, it will not work out. And so you have to take trials. So I use a certain make of filament, which I have been using continuously. Okay, still now I'm not finding any problem. Okay, sometimes these problems, it will not stick to the bed. My bed is sometimes it is not so sticky. I use some acetone and clean it. Just use some acetone, just clean the bed, then deposit. That will work. Sometimes what you have to do is, you have to check the level first. After calibration of axis, you have to check the level. Okay, each whether it bed is bed, you have to calibrate. There are options for that. And one more parameter, what is called z-axis offset. Okay, z-axis offset also you have to check. Okay, this there are several parameters that comes only in practice. Okay, there are a lot of tutorials available, but even though if you see tutorial without any printer available with you, then it is difficult. So whoever is new to this field, try to buy one printer which is costly, which is only 20,000 rupees. Then you will learn a lot of things that will help when you want to do wire arc additive manufacturing. There, that will help, because there is no specific standard machines like polymers. There is no machines for wire arc additive manufacturing. We have to develop our own system. There are systems, but they are very, very costly, in crores. Is it answered? Your question is answered, or you still have any doubt?
Yeah, sir. Very, very thank you, sir. Thank you very much.
Okay. Yeah, please welcome. Yeah.
Thank you, sir. Any other clarifications from participants?
Any questions? Even if you do some research, materials related, anything you can ask. Whatever I covered, even it is not covered here, also you can ask. Whatever I know, I will just share. That is fine. Yeah, you can even post it in chat box. Somebody asked, no, I'm not an expert in textile industry. One slide I just show the demonstration, right? How 3D printing is being used in textile industry. There are some reports says that it's being industried, it is being used in textile industry. No, I am not currently aware of that. Just to introduce you where 3D printer is being used, I just shared that slide. I am not an expert in thing. Yeah, fibers. Currently carbon fibers. There are printers. I went internship for internship in one of the institution where. Wait a minute, I will just read one by one. I'll go. So natural fibers you can still use as chopped fibers. Carbon fibers are being used. Those techniques, in between you can stop. Such printers are available. Composite printers are available. Even maybe I will slide when I present it next time. I will start with that. You can insert wherever carbon you want in the form of chopped fiber or even wires. Continuously, wherever the stress concentration area is there you can just insert the carbon fiber. Machines are available, but a single machine for polymers, it is costing around 24 lakhs. Okay, very simple machine. 6 professors of some US industry, US university, they developed the system. They have a company and they are selling that. I visited a center and I learned from there. You can do that research. Okay, there is a scope. You can do that. What way it is useful to aerospace industry? Aerospace industry, excellent opportunities are there. All these components, whatever I will talk about next session, all metallic materials, right? If it is titanium, if it is titanium, aluminide, nickel aluminide, Inconel, all are no high temperature application, gas turbine application, lot of application you can use. That is one no answer. The how AM is biomedical, I showed lot of applications. Live organ currently it's not that level. Now it is at infant stage. Maybe it will take another 5 to a decade to have such a system for biomedical industry. That is the answer for that. And if you want to start 3D printing entrepreneurs with sculpture, yeah, that is some sculpture you want to fabricate. You can start with reality itself, but people, you can do a search in Google, YouTube also, a lot of videos in Chennai also they are doing. One person from Kolattur, I saw a lot of his advertisement. Since you asked the printer, mostly they use, there is a printer of, manufacturers Eligo. That printer you can use. Whatever printer I have is 220 by 220 into 200. That is a size. 220 by 220 is my bed size. The Eligo is one printer is around 40,000 rupees, where 400 by 400 you can build. The build volume is 400 by 400 platform. Okay, so up to 1 feet, you can go height. That printer is very useful. 500 mm, up to 500 mm height you can go. There are some commercial printers available even 1 meter height. We are making one printer for 1 feet high, 1 meter height. We are developing that. Maybe it will take time, but commercially there are available. Printers are available. Sculptures making are available, but printer alone is not sufficient. Printer, you have to learn printing. You have to learn software. Blender software you have to learn. Then you have to try to learn painting. If you do that, you will become an entrepreneur on that. You have lot of scope for that. See, there are one more thing. Even you can print your photo. You can sit. I got a lot of work on that. These are whatever I'm covering. This is my hobby. Okay, whatever I'm going to cover is my research. That is in the next session. Just to know, this is a fascinating area where you have to start with the hobby. Then you will become master in it. So you can just take your photo. Just you can make a print, right? In a just like a plate, it would look like that. Then set you just LED, just you use LED to just illuminate. You can see your 3D picture. Such a system, such thing you can print and you can learn. Now you can. What are the software tools right now for that modeling? I use Fusion 360. Fusion 360 is free for educators. 3 years, 3 years. You can just rent it. Fusion 360 is the one software which you can use it even for 5-axis machining, inclusive of 5-axis machining. That is the only 3D software I use. You can use any software, SolidWorks you can use, but Fusion 360 is user friendly. So you can easily simulate everything. You can do prototyping. You can do just convert STL, then bring it to Slicer software. Slicer software you have two things: one 3D model, Slicer software. That is two software you need. And you can print. Or you try to code. So if you are familiar with the G code, you can write your own code. You can just bioprinting facility is not available in Sun. We are working on additive manufacturing. Just to show how this is going everywhere. I want to share. We we have a lot of FDM. We have one printer in my center. Just to I bought one. We don't have printing lab. Why is I don't know, network since I switched on the video? Maybe okay. Rasan, you are able to hear it or still
Yes, sir. Yes, sir. But it is breaking, sir. Voice
somebody is telling?
breaking.
Now is it clear or you want
Yes,
to?
sir. Yes, sir.
Is it clear?
Now it is clear, sir.
Yeah. What is the limit of the 3D printing? No, you can. I will show that in the next. No, you can build as much as possible. Polymer printers, no, mostly 1 meter is the height, but metal printing you don't have any restriction. No, especially warm wire arc additive manufacturing is you can build 3 meters. People have done. Limit of dimension somebody asked. Okay, anything else? Maybe you are all tired. 1.5 hours. You sit.
Sir, please share your contact details, sir.
Yeah, it is there. The last slide you can see that, no? Lakshmi Narayanan AK at ssn.edu. Maybe I will come again. I will come again and I will come one more session on 28th. Sir, is it 20? Is it 28?
Yes,
Right?
sir. 28th
Okay.
session 7, sir.
I will cover maybe in between. Some people are coming and talking about solid state, but I will cover with respect to different materials. Whatever research you can get, you can start. All those things I will just share during that session. Okay, if no questions, I will just. Yeah. Somebody is no. Somebody want to ask something.
Not for saving the
இல்ல அவங்க by mistake.
I think, yes, 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 sir.
Yeah.
I think she is not asking any doubt.
Okay.
Okay. My sincere thanks to Dr. A.K. Lakshmanan, sir, for clarifying doubts in high technical manner. Now, we will move to session 2. Before
Okay, thank you.
starting,
I am leaving. Thank you. You have another session, huh?
yes, sir, another session. Here there are two
sorry.
sessions, sir.
Okay.
8 to 9:30, second session will be there, sir.
Okay.
Okay, sir. Per day, we are doing 2 sessions.
Okay. Thank you very much. Thank you. I will meet again. Bye.
Thank you, sir. Thank you, sir. Thank you very much. So before session 2, we will take short 3 to 5 minutes break. Participants are requested to join at 8:15 sharply. You can take 3 to 5 minutes break. Kindly join at 8:15. Yes, now we are moving to session 2, which will be taken by expert Dr. B. Yerumalai, sir. I am very happy to welcome Dr. B. Yerumalai, sir, from Ishwari Engineering College, Chennai. Welcome you, sir.
Yes, sir.
Dr.
Am I audible, sir?
Yes, sir. Yes, sir.
Okay.
Now I request Dr. Radhika Kokandi to introduce our expert.
Am I audible, sir?
Yes, yes, madam.
Yes.
Yeah. Good evening, all. It's my pleasure to introduce about our resource person for session 2, Dr. B. Elumalai. He's currently serving as an assistant professor at Department of Mechanical Engineering, Ishwari Engineering College, Chennai. He has around over 12 years of teaching experience, and his area of expertise includes micro ADM, additive manufacturing, as well as machine learning. It's our honor of inviting him to be a part of this FDP, and now he is going to deliver the session on selective laser sintering, the sustainable reach. Welcome you, sir, and over to you.
Thanks for the invite, sir. And thanks for the brief introduction, ma'am. Let's start the presentation. And we turning off the camera because of the network issues. So, very good evening, everyone. So, it's an honor to be here to discuss one of the most transformative technologies in manufacturing, selective laser sintering, or SLS in short. So, the session is titled Expanding the Frontiers of Sustainable Manufacturing. So, that captures the essence of what we'll cover today. Over the next 1 hour or 90 minutes, we'll go through a journey which begins with the foundations of additive manufacturing, details of SLS process, exploring the materials and physics behind it, looking at real world industrial applications, and then tying all this together under the theme of sustainability, the theme of the FDP. So we know that manufacturing is both the backbone of our economy and one of the largest contributors to the global energy consumption and the carbon footprint. So as we look forward for a more sustainable future, technologies like SLS are not just tools; they are tools for survival. So we have to be sustainable in every aspect of life, especially in manufacturing because it is the largest contributor of the carbon emissions. So we have to make technologies in manufacturing also sustainable. So we'll move on. I am not sure this introductory part will be covered by Dr. AKL also, but I'll just go through fast. So additive manufacturing, as we are aware, it's a modern way of making material by adding layer by layer directly from a digital model or a CAD model. So the basic principles of additive manufacturing, in my perspective, put into 6 different things. Layer by layer fabrication. It's a model-driven process. You need to have a CAD model, so you can play with the CAD model. So to get the product, and material addition, it is not unlike subtractive. It is addition process, and toolless production. So which is a fascinating thing. You need in a conventional production environment, you need to have a specialized tools, cutting tools, molds, dies, jigs, fixtures, all those things. So we don't need to have any tool here. Also, it eliminates the job of process planning. When you need to have tools, we need to have a production plan, we need to have a process plan. But here, just design to manufacturing in between process is completely eliminated. With very little bit of process planning, you need to plan the orientation, you need to plan the layer thickness, all those things. But and you have a design flexibility that is a basic of the additive manufacturing technology, and digital to physical workflow. The entire process is digitally controlled, no need to modify a lot of factors like conventional machining process. And so the ASTM standard uh, is the large leading organization which classifies additive technologies into 7 categories based on the uh, principle how the materials are joined together to make the product. So we have a VAT photopolymerization in which we have a liquid monomer which is converted into a solid wherever the photo interacts with the liquid. So it is photopolymerization process. And we have a material extrusion like extruded FDM kind of material extrusion process. We have powder bed fusion. So we are going to discuss detailedly about the powder bed fusion process. The SLS falls under the powder bed fusion category. And we also have a binder jetting, direct energy deposition like lens processes, material jetting, and sheet lamination processes. So we'll discuss the fundamental of the powder fusion process, or in short SLS. So in in powder bed fusion process, a thin layer of powders is spread across the build platform. A heat source, usually laser in LPBF process like SLS, SLM, or DMLS. In electron beam melting, EBM, electron beam is used as the energy source. So it the heat source selectively fuses particles in the specific regions according to the uh, data from the CAD file. Once the layer is complete, the platform lowers slightly and new layer of powder is spread and the process repeats. Over time, hundreds or thousands of layers build up into a solid part. So the best thing about a PBF is precision. So each layer is be around thin about 20 microns to 100 microns. So that allows you get a very fine detail, complex geometries and excellent mechanical properties. And so the selective laser sintering is comes under PBF, but basically all the processes SLM, DMLS, laser fusing, DM, LM, LMF are different commercial names for the same process, which is laser powder bed fusion. There will be a slight difference in the fusion process or the material distribution thing, but the fundamental remains the same. All comes under the laser powder bed fusion. So these SLS process is developed at the University of Texas, 1980s, and SLS especially works well with polymers, metals, ceramics, and composites. So, and the other thing with the SLS is you don't have to get additional support structure like stereolithography or FDM. So the unsolidified powder acts as the support structure, and that is the best thing about SLS. You know, the process doesn't require any support structure, and the schematic operation of the SLS, so step by step, that we have already discussed, but here, so we'll have a three platforms. So one is powder feed system, and you have a base plate over the build platform on which the powder is deposited, and over which we have a scanning system and a laser which is usually connected to a galvanometer, which controls the fusion path. So these PBF process, SLS, SLM, DMLS, all shares the some basic characteristics. So you need to have a one or more thermal sources. So these thermal sources for inducing the fusion process provide energy for the fusion, and we should have a controlled scanning which ensures only the desired regions get fused together, and a precise powder spreading system which maintains uh, a consistent layer thickness. So you need to the powder spreading system should supply a required amount of powder, and it also spreads the powder in a uniform layer thickness. So together these things creates high precision and repeatability. But there are challenges in the PBF process. So the powder reuse is usually limited for certain cycles. Often it is reused, but after some cycles you have to discard the powder. And usually all the PBF process produces parts with porosity, and the thermal nature of the process causes thermal stress and the distortion. So, despite these challenges, SLS is one of the most industrially adapted AM process. Because uh, it can print polymer, ceramic, as well as a metal. So, uh, any process, like any process, so there are certain process parameters which needs to be controlled to get the required quality. So these process parameters are usually put into these four categories. One is these laser related parameters like laser power, spot size, what the pulse duration you're using, what is the pulse frequency you're going to use, and the scan related parameters like scan speed, how fast your laser is going to move, scan spacing, what the hatch space, what is the scan pattern you use, all those scan related parameters and powder related parameters like particle size, shape, and its distribution, powder bed density, layer thickness, and the powder, the material property of the powder use, all those things, and the temperature related parameters. So, what temperature you maintain the whole environment, what is the powder bed temperature, what is the feeder temperature, what is the environment, whether you use it inside the inert gas environment, all those things matters. So, see, in a laser related parameters, the laser power is the main thing. If the laser power is too low, we get lack of fusion. Powders won't get fused together, and the particles don't burn properly. And if the laser power is too high, we risk keyhole porosity, where the excessive vaporization creates gas bubbles inside the layers. And about the scan speed, again the same. You have to optimize the scan speed. Too fast, bonding is too weak, and too low, overheating occurs. And the powder size also affects the packing density. If the powder is very fine, the packing density will be high and reduced porosity. If the powder is more coarse, packing density will be less. So the powder size affects the flowability of mold pool, the surface finish of the finished product, and optimizing the parameters reduces the defects. Next we'll discuss the hardware part of the any powder bed fusion machine. So the basic thing is a laser system. So you need to have a high powered laser which is usually directed by galvanometer mirrors, and we the machines are generally use CO2 as well as fiber lasers, and we have a scanning system, galvanometer based scanning system, the powder delivery system, powder deposit system, and build platform, and a base plate. So usually in powder bed fusion, over a build platform, we have to place a base plate on which the product is built, and you have to cut and separate the base plate from the workpiece. So, and powder removal, gas supply, and filtration system also. It has to capture the unused powder. You have to supply some inert gas and recycling system, all those hardwares they work together. So the system should work in harmony to maintain the controlled and repeatable environment. So this environment affects the product quality, its defect-free nature. Now we'll discuss about the different materials that can be printed in a SLS or any other PDF process. So basically, in SLS of polymers, we'll go with PA11 or PA12 polyamides, polystyrene, PET. So all those peak kind of polymers are used, and its composites also possible. And metals, almost all the metals, steel, titanium alloys, nickel-based alloys, few aluminum alloys, copper alloys, cobalt, kind of metals and alloys can be printed, and also metallic composites can also be printed. And the ceramic composites are infant stage. There are some developments in ceramic printing. There are some processes for printing ceramics that we will discuss. Now we move on to the powder fusion mechanisms. So basically, any PBF or SLM process uh, uses these four powder fusion mechanisms to fuse powders together to get a solid product. So we'll have a solid state sintering in which the powders gets heated just below its melting point, so they flow and fuse together to the adjacent powders, adjacent particles. And we have a liquid phase sintering and partial melting, so in which you have a two or three different powders together. So liquid phase sintering means one powder gets completely melted and another powder is still in the solid form. So the molten uh, powder binds the powder together to get the solid product. And we also have a full melting. You need to have a single component based on single material or sometimes alloys. So the alloy powder or single component powder completely melted and get the product. We also have a chemically induced binding in which some chemical reaction takes place and it forms the powders bond together. And these uh, different materials undergoes different types of powder fusion mechanisms. In polymers, we generally use solid state sintering. The polymer powders gets heated just below its melting point. Also, we have a liquid phase sintering. We need to use a polymer plus a binder. The binder is getting heated, and because of the binder, the powders getting together. We also have a full melting where a single polymer is brought to molten state and then fused together. So we have a different, basically two different types of polymers, which is generally used in SLS or PBF process. So thermoplastics, we have a semi-crystalline and amorphous. So we only can use thermoplastics, in which we have two different categories. We have a semi-crystalline thermoplastics and uh, amorphous thermoplastics. So in the like polystyrene kind of amorphous thermopolymers, they have a, you can see the temperature versus relative volume curve. The amorphous polymers have a wide range of melting, where the semi-crystalline polymers have a sharp temperature point. So, though the semi-crystalline polymers produces stronger part, for printing a semi-crystalline polymers, we need to maintain the temperature to the point. So the precision of the temperature, everything in semi-crystalline plastics, printing it. But in as amorphous, the range is a bit wider. Then we have a different kind of semi-crystalline polymers. We have a polyamide, and we also have a polyoxymethylene, generally known as POM. So you can see the surface finish. So we produces better surface finish because it undergoes full melting, whereas a PA produces a rough surface. And different types of polymers process we use to get different applications. The semi-crystalline polymers like PA12 or POM, they are semi-rigid polymers. They are used for long-term applications. And amorphous polymers usually used for investment casting kind of glass pattern applications. They are accurate, but they are porous, so they are used as the last pattern in investment castings. So, and we also have some other polymers like sacrificial polymers that are generally used in metal printing or ceramic printing as a binder, and semi-crystalline polymers filled with some glass fibers or copper particles also
Hello.
can be used. Yes.
Yes, sir. Good evening. Sir, biodegradable material, we are sometime in some conference I have seen this thing. But can polymer and biodegradable material can be sandwich for this additive manufacturing process?
I'm not getting your question, sir.
Bi-
Biodegradable
biodegrad-
polymer.
biodegrad- and biodegradable material.
Okay.
Can it will be mixing and we can able to make any material which can be used for, as an additive material, so that it can be easily biodegradable.
Yes, sir, it is possible. In case of FDM, you can make easily make filaments based on the biodegradable polymers. Then you can print. In FDM, this process is very simple. So you can make filaments out of the biodegradable polymers and you can print it. But in case of SLS, what we are discussing here is you need to have a polymers in a powder form. So getting the polymers into uniform powder size and powder form is quite difficult. That cannot be done with the faculties or with the available facilities. That powder should be supplied by the machine manufacturers. That powder size, powder distribution is very important thing in SLS.
Okay, sir. Okay, sir. Thank you, sir.
So here we'll discuss about the debindable polymers where we have seen here. So in which the polymers are used as the binding thing mixed with some other usually glass, ceramic or metal parts. So they are printed together in SLS. Then they put inside oven or a furnace. The polymer gets melted away, and the remaining ceramic or metal becomes a solidified part. And we also have a reinforced polymer powders. So usually you can have a PA glass is a general thing. PA glass means you have a polyamide mixed with glass beads and sometimes elongated glass fibers also possible. So these glass beads sometimes are aluminum beads, gives you a better strength than a simple polyamide can provide. And elastomeric polymers that have elastic properties that can also be printed in SLS. So usually in SLS, these green part printed with a basic powder which is rigid. Then the polyurethane is infiltrated to get the elastic property. So this is about polymers. Now we'll discuss about metals. Again, metals, all the four fusion mechanisms are used based on the requirement. So solid state sintering, as we know, is used, but usually metals to get the dense part with less porosity, we have to go with either LPS, partial melting, or full melting. Sometimes LPS means you will have two metals together. So you can see here we have a steel plus copper, where copper is having less melting point. It melts before steel. So the steel will be still in the solid form, and the copper is getting into liquid form. So the copper acts like a binder, and wherever the copper gets melted because of the laser heat source, we'll get the sintering here. We'll get the fusion here. And also like tungsten, cobalt, tungsten, copper, these kind of composites or these kind of things can use the LPS or partial melting thing. You can see the same image. You have a FeCe powder mixture. So the Fe is like acting as a reinforcement like in a composite, and the copper powder makes the matrix here. And you can also have a full melting, like you need to, if suppose if you want to have a pure metallic part out of the PBF process, that will be melt to its melting point, then solidified. So like if you want to have a pure titanium, and there are alloys also, you can go for the full melting. So full melting gives you a denser part. So the porosity thing is issue with the all the PBF process, where full melting almost reduces the porosity part, and where we can also have a chemical binding in a metallic SLS process. So here I presented aluminum, magnesium based metallic printed component, in which the nitrogen atmosphere, which chemically uh, forms the powder into solid because of the chemical bonding process. And next we'll discuss about the ceramics in SLS. Like ceramics present a different challenge for SLS. Unlike polymers and metals, ceramics have a high melting point and very low thermal conductivity. So they require a tremendous amount of energy to sinter or melt, and they tend to crack under high thermal gradients. Still, ceramics are attractive because they are lightweight, wear resistant, and withstand very high temperature. So there are different approaches to print ceramics. So we can have a different consolidation types based on the ceramics. So for a silicate ceramics, we have a liquid phase sintering, we have partial melting, full melting kind of things. Oxide ceramics you can print, you can also print non-oxide ceramics. There are different approaches. The one approach is indirect SLS, in which you don't have to completely melt the ceramic. You have a ceramic plus polymer binder, and the polymer binder gets melted, and it binds the ceramic parts together. Once the printing process done, then the debinding takes place inside the furnace, where the polymer gets removed and the ceramics gets uh, you know compacted. But using the indirect, when you want to use the indirect SLS process, you have to consider the reduction in all the dimensions while designing the component itself. And you can also use full melting. The direct SLM also can be used for ceramics. The SLS of ceramics slurry is also possible. You can also use different types of composites. You can have uh, a polymer metal composites where a polymer matrix holds metallic particles. They're generally used for electrostatic shielding applications. And we have a polymer ceramic composites for biomedical scaffolds, which require toughness, and with the bioactivity of ceramics, you can also have a metal ceramic composites, for high temperature and very resistant applications. So we know the advantage of composites. You can tailor made the required product. So in the sustainability perspective, the composites also have a great potential for the reduction in weight and high lifespan kind of things, which reduces the carbon footprint and the increases the sustainability perspective. Now that we have discussed the fundamentals of or the foundation of powder bed fusion process, and we have discussed about different mechanisms for different materials, how they are formed. Now we will discuss the physics of basic physics of the powder bed fusion process. So the uh, the heart of the process is the melt pool, a small region where the laser interacts with the powder. So the melt pool only have a small size, if you usually tens of microns, but it determines the properties of the final part. So you need to understand how the energy transferred from the laser to the uh, powder, then it's converted to liquid, how the liquid reacts to the energy, and how the solidification takes place, how the energy is transferred back to the environment while solidifying via thermal radiation and different mediums. Then we need to understand the gas phase flow in the fusion process. When the laser hits the powder particle, not only the powder gets melted, sometimes the gas flow, that uh, molten metal induces a gas flow from the molten pool. So that needs to be understood to control the process. And the melt pool dynamics, how the uh, material reacts, how the material acts at the molten state, how it flows inside the melt pool. No, uh, it now we can see now very intense phenomena inside the melt pool: melting, solidification, fluid flow, vaporization, sometimes small explosions also. So you need to understand the multiple dynamics to improve the quality, reducing the defects and making the process more sustainable. And the heat transfer part that we have said before, how the heat is transferred from the laser to the powder. Powder becomes molten state. Molten state powder to the heat has to be ejected from the molten pool so that the powder gets condensed, right? So the condensation process also very important. And the process stability. So you need to control the layer thickness, you need to control the scanning speed, you need to control the laser power, laser pulse, laser width, all those things to get the process stable. And again, the thermomechanics while heating the uh, molten metal has different uh, stress, right? So when the powder gets melted and again it's get solidified, so the concentration of thermal stress, uh, combined tension and compression stress makes the uh, part weak. So we need to relieve the stress, right? So the physical process of the SLS starts with the laser interacting with the powder and vapor ejection or gas flow, and the melt pool and the surrounding powder, how it reacts. These dynamic, creates a spattering effect, as we can see one of these images. You can see this evaporation induced vapor jet from the milk pool, and the laser and the spattering of powders surrounding the milk pool. Here also we can see around the melting track or printing track how the powders ejected from the thermal stress.
आमच्या घरात खाली मी अशी बसली त्या पेरूवर
So those things need to consider.
गावात नाही पिळत आहे ती सगळी इकडं अगं
So these complexity of the process is needs to be understood, so that while designing and while printing, the perfect or optimized parameters are used to get the perfect product. Then we'll discuss about some of the design challenges in powder bed fusion. Again, this step effect or staircase effect is common for all the additive manufacturing processes where you need to have a print layer by layer. So the uh, staircase effect is unavoidable. So if you want to reduce the staircase effect, you need to reduce the layer thickness, or you need to adjust the z-axis based on the required surface finish on different faces. And the another issue apart from the stair step effect, you need to you need to understand the particle attachment here in the SLS or SLM process. So the mold pool attracts the surrounding unmolten or solid particles. That solid particles usually attached with the part built. And also the upward facing surface has a different property than this downward facing surface because of the particle attachment. So while designing and while orienting for printing, you have to consider these two factors. One is stair step effect and the particle attachment effect. Next, we'll discuss about the porosity in laser powder bed fusion. So the porosity is an unavoidable issue in a powder bed fusion process. It is perhaps the important defect in SLS that you need to optimize all those process parameters to reduce the porosity. So there are uh, basically two different types of porosities. One is uh, like a fusion porosity where you used less power, or the opposite side is gas porosity where you used high amount of power. So the figure displays two different types of porosities. The figure which is in my left side is like a fusion, and the right side is keyhole porosity. The lack of fusion porosity is due to the less amount of power source used, whereas keyhole porosity is because of the high amount of energy used. So, the porosity reduction can be done in two ways. One is, better parameter control. We can directly improve the quality. Also, you need to have uh, a good post-processing setup, so that you, after printing, you do some post-processing which may reduce the porosity component. And you can see in here the interaction of different hatch tracks also sometimes causes porosity. So these are unavoidable in SLS process, and you should have a proper porosity mitigation strategies when using the SLS process. As I said earlier, you have to optimize the laser power and scan speed so to achieve the stable milk pools, and preheat the powder. So the powder powder supplied powder should have a basic temperature. Preheating is necessary sometimes to get the appropriate thermal gradient, and you need to use a smaller and more uniform spherical powder. So the powder, how small it is, more dense it is. So better packing will reduce uh, powder this porosity effect, and remelting sometimes. So melt again the layer. Sometimes it will help in densifying the layers. And hot isostatic pressing is one of the uh, post-process technology which is generally used with SLS to get the density increased or porosity reduced process. And you can also have a sharp cleaning and surface processing so that the surface level pores gets removed. But these every strategy has a cost, and for example, so for example, these post-processing things may reduce a defect and will increase the microstructure. But in the sustainable perspective, you need to reduce the pores before printing. That means you need to have a proper design, you need to have a proper parameters, you need to have a proper powder. The post processing, most of the time it is necessary, but you can reduce the amount of post processing required. The post processing, usually we have a different types of post processing, like surface level post processing. We have a heat treatment, we have a hot isostatic pressing. Usually these three post processing are sometimes often required for any SLS part. That is one of the major disadvantage of the SLS thing. You definitely have a post processing, one or other post processing is definitely required. These to increase the improve the surface roughness for dimensional accuracy. Mechanical post processing is generally used, but the thing is you need to identify the exact post processing to get the required surface finish, required accuracy of the product, and to get the desired microstructure to reduce the porosity. Also, you need to get the better post processing. So usually, there are 3 or 4 types of surface treatments are used. We can have a mechanical surface treatments. You can have a sandblasting or bead blasting. So fine particles blasted against the surface to remove loose powder and surface roughness. Grinding and machining can also be used, and these methods are effective, but they generate waste. Because in short cleaning or sandblasting, you use abrasives that are consumes energy as well as it produces dust pollution also. And you can also have a chemical electrochemical surface finishing. In electrochemical polishing, usually a part is submerged in an electrolyte and the electrical current is applied, as we know. This commonly used for stainless steel and medical implants, because medical implant and things require high amount of surface finish, and they need to be corrosion resistant. So usually electrochemical polishing is used for biomedical applications. And you can also have a laser based surface processing. Like laser polishing is nothing but using a low power laser that melts the top layer or top surface of again the molten layer re-solidifies. Sometimes it smooths out the peaks and valleys, which creates the uniform surface. And in general, the SLS parts will have a high amount of thermal stress. To relieve the thermal stress, we need to have a proper heat treatment. So usually the 2 types of common treatments are used in SLS. One is stress relief annealing, hitting the part to a moderate temperature and to relieve the residual stress. Or aging or hardening treatments also used. for alloys like margin steels. And finally, we have this most important post-processing technology for SLS or any other powder bed fusion process. Sorry. So it is hot isostatic pressing or hip. In hip, the part is placed in a high pressure, high temperature chamber, which is usually filled with inert gas. So the pressure of isostatic means all the directions, same amount of static pressure is applied. So these pressure forces the material inward, which close the internal pores and defects. So these usually results in a near fully dense part with mechanical properties close to the forged or sometimes exceeding the forged components. These HIP is widely used in aerospace and medical applications where the safety margins are very critical. It's again HIP is very energy intensive, uh, but for producing defect-free and long-lasting part, the HIP ensures that the material or the part is highly improved in the perspective of removal of defects inside the component, where the mechanical and other surface treatments only remove defects or improve the surface finish, whereas the hot isostatic pressing removes the pores inside the component also. Now we'll discuss most of the few industrial applications. Uh, uh, in aerospace, like aerospace is one of the earliest and strongest adapters of the SLS and metal additive technologies. Uh, as we know, weight is everything in aerospace. Every ounce or every gram of reduced weight costs thousands of liters of fuels. So not only this economic perspective, but also massive reduction in the carbon emissions. So every kilogram reduction in weight in aircraft or space things reduces the carbon footprint also. Uh, you can have the famous example of General Engineers G's LEAP engine nozzle. So this LEAP nozzle was made out of 20 separate components that has to be assembled together. But with SLS, they were able to produce that LEAP nozzle with a single lightweight optimized part. It was also 25% reduction. You can get this LEAP example through Google. And Airbus also used various SLS brackets, cabin components, and structural fittings. Like NASA also tested these AM-based rocket engine injectors also. So these aerospace industry is the adapter of SLS technology in a massive way. Next comes the automotive sector. SLS, in a decade, it moved from prototyping to production. You can see this Bugatti example. This is a standout Bugatti titanium brake caliper. It is produced by SLS process. It is the largest functional titanium component ever printed. So it is capable of standing high amount of force compared with conventional calipers. And the BMW also established an entire AM competence AM center. SLS also used in various automotive industries. Uh, in automotive industries, again, lightweight, customized components are required. And rapid prototyping also used in automotive industries to reduce the design cycle time. And in energy sector, SLS used to produce turbine burners, heat exchangers, and other high performance components. Siemens used SLS to print gas turbine burners, and we also have medical applications in SLS. we know that every patient is different, and SLS, customized implants are needed. So SLS allows implants and devices to be manufactured to each individual's anatomy. And titanium bone implants, dental bridges, and cranial plates are usually designed from CT scans and printed for exact fit. So beyond implants, polymers like nylon and TPU are also used in surgical guiding process. Prosthetics also printed in SLS. You can see other applications like consumer products, lifestyle applications, architecture and construction applications, defense and military applications also. About different applications of SLS. Industrial industrial tooling and jigs also produced using SLS process. Now we'll move on to sustainability and the environmental impact of the SLS process. So these slide presents the LCA studies of the environmental impact of any product. So especially in SLS, you need to get the raw material extracted. In SLS, the raw material is of a powder form. So there are different ways to get the powders. That is very difficult for a metal to be converted into powder. So there are they are highly energy consuming processes. So where the energy required to convert the solid metal into powder is very high. So there the environmental impact comes into picture. So that the processing and use phase also energy consuming process. SLS uses high energy laser which consumes high amount of energy, so that have an environmental impact and have a carbon footprint. And in sustainability perspective, sustainable utilization of the material in SLS, you can reuse most of the unused powder for certain amount of cycles. Uh, the sustainability usually, sustainability usually have three things. One is environmental, so you have to reduce resources, uh, reduce emissions, reduce waste. And in the economic front also, you need to have get value while printing it, and the social sustainability also important. So the SLS addresses almost all the things of all the pillars of sustainability. In SLS, we use less material, so less material waste is used. So lightweight design, which offers, in aerospace, in automotive industries, the lightweight materials reduces the amount of fuel consumption. That addresses the environmental sustainability thing. And economic sustainability, the reduction in tooling cost, faster time to market, and localized production, which you know reduces the economic load, which improves the economic sustainability. And social perspective, these better healthcare through the custom implants, improved accessibility through the advanced products, the better improvement in supply chain, all those things addresses the social perspective of sustainability. And the material utilization and waste generation in SLS can be understood. The material efficiency in SLS is the strongest advantage in SLS sustainable perspective. So we know that the traditional machining can waste about 70 to 80% of material, especially with some really expensive alloys. But in SLS, the unused powder can be recycled, sometimes 80 to 90% reuse, depending upon the material. Uh, Sometimes you need to add virgin powder to maintain the quality, but the overall waste is far lower than the subtractive process. For polymers like PA12, recycling rates are very high. And, they know they are making the PA12 is cost effective and environmentally friendly material. And next we will discuss about the energy efficiency in SLS. So one of the main characteristics, one of the main criticism of SLS is its energy consumption. So lasers and heated powder beds require significant amount of power. However, when we evaluate the sustainability, we must look at the entire life cycle. A part that consumes more energy during production may save, far more during use. Say, for example, take a lightweight aircraft component produced via the SLS process may consume more electricity while uh, printing than it consumes when you produce the same component during machining. But over the years of service, the reduced fuel, that compensates the energy spent during the printing. So the if you conduct overall life cycle analysis of the SLS components, you can have a you can see the energy efficiency is high in SLS when compared with conventional machining process. So you can see here, we compare the energy during the material production, during manufacturing is comparable to the CO2 emission and energy consumption of the conventional process also. So again, this slide represents the contribution of different stages of the environmental impact. You can see the energy consumption during the material preparation is very less, but 24%, and the energy consumption during the atomization stage is 49. That means the solid to atomized, the powder conversion consumes 49% of the total energy for the SLS process. Whereas, so to summarize this, there are sustainability advantage of SLS process. We have a material efficiency, so minimal waste and high powder recyclability, and light weighting can also reduce the energy usage. But we need to adapt some sustainable, strategies for the sustainable manufacturing. It should starts from the material selection phase. uh, you need to have environmental friendly materials, that is, you recycled powders. Suppose if you want to print a polymer product, you can produce the powder from a used polymer component, or you can have a bio-based powders. So you can have a environmental friendly powders. And you also, while selecting material, you have to consider the life cycle consideration, how the powder is going to be extracted while producing the powder, how much energy is to be used, and how it is going to be disposed. That is end of the life also you have to consider while selecting the material. And you need to optimize the process so that it reduces the energy consumption, while maximizing the material utilization by optimizing the process parameters. You can also optimize the scanning strategies so that you monitor the printing process. Then optimize the design stage itself. So while optimizing all those things, you can able to reduce the waste production. You can increase the sustainability of the product. And how you're going to handle your waste. Waste in the sense, sometimes after some cycles you cannot reuse the powder, so that unused powder goes become waste. How you're going to use it? How you're going to recycle it? Right? We're going to be sometimes you have some flawed components, some fractured components. How are you going to recycle it? Whether you're going to convert that powder again and print it again, or are we going to dispose all those things? That waste management also has to be considered for the sustainable perspective as well as the environmental perspective. And you can, when you think about the sustainability as well as environment, this is quite straightforward. You have to integrate renewable energy into the SLS process. I think we are 9:17. Okay, we go fast. Design for sustainability. So you have to design lightweight. Part consolidation is a very good strategy in which you print multiple parts in a single setup, and the material efficiency while orienting without support structure, different orientations to get the different optimal material usage will give you sometimes more reusable powders. And collaboration between the researchers, manufacturers, as well as the policymakers will definitely play a role in not only in SLS, in all the manufacturing processes, which reduces the carbon footprint and increase the sustainability. So, so far we have discussed about the basics of SLS process and the powder bed fusion technology altogether, and different materials that can be printed in SLS, different fusion mechanisms that are used in SLS and other powder bed fusion technologies, the physics behind the powder bed fusion, how the powder is converted into solid, how the multiple dynamics should be considered. All those things we have discussed. And I will move on to the possible trends in future or emerging trends with the perspective of sustainability. So, recent SLS printers will have a multi-laser and a high speed system. So, instead of a single laser, it scans a layer one hatch at a time. You can have a multiple lasers. The new systems will have multiple lasers and high-speed scanners, and you can also integrate AI and real-time monitoring into the process so that you can monitor the printing process in real time. And bio-based polymers, they are reducing the fossil-based feedstocks. So bio-based polymers can also have a reduced carbon footprint, reduced environmental impact, and a closed loop recycling system. So you can continuously use the unused powder. So these strategies are under the research stage. And we can also have a hybrid manufacturing in which combining of SLS with machining. In the same setup, you print and you machine. This for better efficiency. So this each of, and you can also have a new allies, new powders into the market. New powder research are in research stages, and there are different post processing. There are different proposals for improved post processing, and different strategies to automate the SLS process and quality control of the products. So each of the future trend may strengthen the sustainability argument of SLS, making it kind of green manufacturing. So I will conclude uh, the presentation with these remarks. So the 20th century, we all know an era of mass production, but the 21st century is going to be sustainable production, where decentralized, intelligent, and it's a circular uh, economy. So decentralized means you don't need to have a mass production industries. The customized products can be printed in a decentralized printing stages. So SLS is not only the tool for the transformation from mass production to decentralized sustainable production, but is also most powerful tool. So by embracing SLS kind of advanced manufacturing technologies. We are not only advancing the technologies, we are also taking responsibility for our planet so that we leave the planet for our future generation in a better place.
Very nice information, sir. Thank you.
Any queries from the audience?
Sir, it's a very informative session. We are getting new things from you for the implementation of our research, sir. Thank you.
Thank you.
Any other clarifications from participant side?
So it's 9:20, sir. We can call it a day.
Okay. My sincere thanks to Dr. B. Ermali sir for delivering detailed core concept of selective laser sintering with design challenges and sustainability environmental impact with strategies for sustainable manufacturing. Thank you, sir.
Thanks for the invite, sir. Thanks for the question participants.
Sir, contact details will be shared later. Now the feedback link will be circulated. Participants are requested to give feedback for both sessions with a single link. So you can give feedback by using the above link, which is available in the chat box. So tomorrow, 6 p.m., the session 3 will be started. Thank you all. Thank you.